Now we will talk about standard normal complementary CDF. Tables of z-score are useful. Tables of z-score are useful for obtaining numerical values of integrals of a Gaussian PDF over intervals near the expected value. What it means is that if our values are within the limit of this first deviation, second deviation, and third deviation, then we can use this z-score easily. We can find the probability easily in that case. Regions further than 3 standard deviations from the expected value are in the tails of the PDF. As you can see over here, when we go beyond this third deviation, then it is in the tails of this distribution. So when z is greater than 3, where in other words, when the probability which we want to find goes beyond this third deviation, then f of z is very close to 1. For example, f of z of 3 is equal to 0.9987 and f of z of 4 is equal to 0.9999768. In many applications in communications and signal processing, QZ, which is standard normal complementary CDF, is slightly more convenient than to use f of z of x. So keep in mind that QZ is the probability that a Gaussian random variable exceeds its expected value by more than z standard deviation. What it means is that whenever we have to find the probability up to this third deviation, then we use this normal z-score. But if it goes beyond this third deviation, then we prefer to use standard normal complementary CDF. So f of z is an increasing function from infinity to 1, as we have seen before. But since q of z is equal to 1 minus f of z, or complement of f of z, it is decreasing function, or it is from 1 to minus infinity to infinity. So it goes from here to here in z-score, from minus infinity to 1. But in this case, it goes from 1 to minus infinity, from right to left. So therefore, the limit of integral of q of z is z to infinity instead of minus infinity to z. We can see that here in this integral, the limit is now from z to infinity, whereas before it was from minus infinity to z. In many applications in communications and signal processing, q of x is slightly more convenient to use than phi of x or f of x. You can say this f of z. So let's see an example over here. In an optical fiber transmission system, the probability of a binary error is q under root SNR divided by 2. What is the minimum value of SNR that produces a binary error rate not exceeding 10 to the power minus 6? So we are asked to find q of z which is less than 10 to the power minus 6. Using complementary CDF table, we find q of z less than 10 to the power minus 6 when z is greater than or equal to 4.75. So we look over here. For example, 10 to the power minus 6 here, it is 10 to the power minus 6. So z is 4.75. And so therefore SNR under root SNR divided by 2, if it is greater than or equal to 4.75. So if it is less than 4.75 over here, then the error rate will be more here. But if it goes above 4.75, then we can see that the error rate will be less. So under root SNR divided by 2 must be greater than or equal to 4.75, and we take a square on the both sides of the equation, then SNR under root divided by 2 whole square and 4.75 whole square gives us SNR divided by 2 equal to or greater than or equal to 22.5625. And if we just simply multiply this 2 over here, then we get 45.125. So If SNR is greater than or equal to 45.125 dB, then error rate is less than 10 to the power minus 6. Erlang random variable. This is x is an Erlang random variable. If the PDF of x is given like this, f of x is equal to lambda raised to power n, x raised to power n minus 1, e raised to power minus lambda x divided by n minus 1 factorial. The Erlang n is equal to 1 comma lambda random variable is identical to the exponential lambda random variable. Just as exponential random variables are related to geometric random variables, the family of Erlang continuous random variable is related to the family of Pascal discrete random variables. Let k alpha denote a Erlang a Poisson alpha random variable. For any x greater than 0, the CDF of Erlang n comma lambda random variable is given as f of x is equal to 1 minus summation k 0 to n minus 1 lambda x raised to power k e minus lambda x divided by k factorial.